So I just want to go through some basic stuff in R that we can use R to help us visualize, which is really the best way to look at our assumptions. We don't have a lot of statistical tests around our assumptions. There are a few out there. Mostly we get it from looking at our data. So first I'm just going to kind of prep the battle space here. I'm going to load up the packages that I'm going to need and set the working directory. Okay, so now I'm going to create some moderation data. And what I do is I'm actually creating a data set. And we won't get into all the details about how I'm creating that. Oops, I missed that last parenthesis. Okay, so I've created a data set DAT, 100 observations of 3 variables. Now, LM1, you'll see what it is. So it's we have 3 variables, y, x, and z. So LM1, we can just do the additive regression of that. And if we look at the summary, we can see that x and z are both significant related to y. Now, if we look at the moderation, where y is regressed onto x times z, now we can see that, yeah, there's moderation going on here. In fact, x and z independently don't have an effect. It's only the moderator that has the effect here. So we should see some very strong violations of the assumptions when we don't include the moderator variable. And so let's take a look at that. First, let's take a look at the scatter plot, right? So our scatter plot of just x and y. And you can see here, this looks kind of okay. Although, if you look, there's a little bit of a cone going on there. This is a classic sign of heteroscedasticity, that the variance is not constant, right? So remember that the variance of the residual should be constant. So let me add in some labels, and then let me add in a smooth line and the line of best fit. So the errors for any particular person, or for any particular value of x, the errors should be the same, should be constant. But instead that we see that there's in fact this cone shape, which suggests that the errors are not constant across different values of x. This is heteroscedasticity. And in fact, if I look at my interaction plot, I can see that, yes, there is in fact some heteroscedasticity, right? We see the moderation happening right here. There's an additional way to do some data visualization. That's the pairs function. And let me show you what that does. That creates bivariate correlations among all of our variables, right? So we have x, we have y, and we have z. So here, and these are just mirrors of each other. So here's the bivariate correlation of x and y, the bivariate correlation of x and z, and the bivariate correlation of y and z. And I can even add lines to each of those plots, right? And that gives us some idea of what's going on with these. And then we can start to look for those cones that may suggest some existence of heteroscedasticity. I can also look at histograms of my data with the function hist, right? So here's my histogram of the x data. You can see that kind of looks a little bit skewed. Same thing for the y, a little bit skewed. Now, it's never going to be perfectly normal, but we can look for at least a little bit of that. Z actually looks kind of okay out of all of these. But really, most of our assumptions are more about the residuals and the errors than they are about the set of data themselves. So we can plot the residuals. Let me show you what that looks like. If I just regress y onto x, right, I create a model for that, and I can plot x onto y. So we've seen the bivariate. Now, let me show you what happens when I plot LM1. So I'm plotting LM1. Now, you look here, it says I have to hit return to see the next plot. And now you can see over here, I have these plots. I have residuals versus fitted. I have the normal QQ plot. I have the scale location plot. And I have the residuals versus leverage plot. Let's go through each one of these and show what they mean. Now remember, way up here, LM1 was my additive, right? So this did not include the interaction term. LM2 included the interaction term. So we should see some violations of assumptions with LM1 because we know that interaction term is important. So let's see how that plays out. If I look at my residuals versus fitted, here in my violated, where I violated the assumptions, my additive plot, you see this U shape to this. Now, what are we getting here? Our fitted values, right? So these are our expected values, our y hat versus the residuals. We should not see this U shape. This suggests that the residuals change depending on our fitted values, depending on our value of the expected value of y. Now, if we include the moderator variable, what we get is this nice, more or less straight line for our fitted values versus our residuals. You see the difference between those two? Here we see some sort of relationship. Here we see almost no relationship between the fitted values of the residuals. So this suggests that this second plot, this second regression equation is not violating any assumptions. Now, let's look at the QQ plot. The QQ plot is about the normality of the residuals. Remember I said that the residuals should be normally distributed, and that's what the QQ plot does. It actually means quartile, quartile, right? So this is a histogram of the residuals. Look, that doesn't even look normal, right? As opposed to a histogram of the residuals for my second one, now that looks a little bit more normal. And if I plot that QQ plot, look how this has kind of this, it looks okay through here, but here at the extremes of my theoretical quantiles versus my standardized residuals, I see this start to drift far away from this theoretical dotted line. Now, I should see less of that here. So look down here, it's actually a little less extreme. It's still kind of a little bit of a mess at these higher quantiles, but here at these lower quantiles, that's kind of gone away. Now, scale location is the plot that I actually get a little bit more out of. See, again, my fitted values to my square or my square root of the standardized residuals. Again, I have that U shape, whereas for plot 2, I have a very flat shape here. So this, again, that's kind of what I'm looking for when I'm looking for homoscedasticity. It should look something like this. If I go back to this other plot, the fact that there's this U suggests that we don't have homoscedasticity. And then the final plot, leverage, is about how extreme certain values are. That really doesn't do us too much in the data set that I've created here, but leverage is the residuals versus leverage. Leverage is how extreme the values are. So if we look at that, and technically Cook's distance tells us if something is outside of Cook's distance, that would tell us that that's an extreme value. None of these look particularly extreme here in either one of our plots. So that just tells you what that fourth one looks like. But if we're looking to test our assumptions, we really want to look at these plots of the residuals to give us some idea about what we're doing. So data visualization, this is just to give you a taste of data visualization. It can tell us something about whether or not our assumptions are violated. But again, this is a case where we really need to know our data. We really need to go back and look at our data and understand how it's plotted and how our data is related to each other and how our residuals of our regression equations are related to each other.